Hello everyone, my name is Li Tingxiao. Here is my teammates Feng Li and Lin Yuxi. Today we're gonna introduce our project, Generate Captions from Images, which is a neural image caption generator. We also referred to the paper Show and Tell, a neural image caption generator. Okay, first for the introduction. In the last presentation, we remembered that our group crawled down pictures of corgis from the website and made two applications. One is the word cloud and one for photo mosaic. But sometimes the images we crawled down did not have clear titles to describe the images, and sometimes they were even grouped. So in the project, our group want to build a model automatically generate captions for the images to describe the content of the images. For example, the picture for the artificial description can easily described as a dog is standing on the grass. We want to automatically description for this picture through the neural network like CNN and RNN, so that's our main point too. Then the main steps in our mission are as follows. First, for the pre-processing part, we resize all images from the dataset. Then we build the vocabulary to form language model. Next, we training the model, include the language model and the visual model. Then text and generate caption. For the first step, collect thousands of different images for training the model. Ensure accurate description for this picture. We resize all images into 256, multiple 256. That make more easier feature extraction. In order to solve, for example, to help disadvantaged groups, such as the elderly and the visually impaired, to better understand the content of images on the web. Such real-life practically problems, we have to implement a very challenging task, which is to use correctly formed English sentence to automatically describe the content of images. The topic is not simply a matter of implementing an image classification and recognition task. We need not only a visual model, but also a language model that can perform semantically description. Indeed, the description must not only capture the objection contained in the image, but must also impress the relationships between these objections, as well as their proportions and the activities in which they are involved. In our group work, we propose a generative model. The generative model is based on an architecture that combines recent advances in our computer vision and machine translation. recent advances in the vision and machine translation can be used to generate neural sentences. Describing can be used to generate neural sentences describe the images. Instead of splitting the above task into sub-problems and stitch together exist solutions, we would like to propose a singular giant model. We choose to use the CNN and the images encoder. First, pre-training it for the image classification, and use the final hide layer as the decoder for this input to the RNN to generate sentences and achieve captions for the images. Our contribution is as follows. We can use additional data for pre-training, since our model combines a visual subnetwork and a language model. Well, today we have a very good article, which is using this recurrent neural network to provide this attention information. Then come to the instructor machine to look at the pictures and then summarize them into paragraph. Then we can put it into the machine, and the machine will see that there is a bird flying on the water. So what about machine which is able to express so brilliantly this insight it has on the picture? Then we can still feel that this machine is interesting. We will talk about the AI is able to do this above. The figure 1 is an architecture of the overall network. Then the graph first goes through the Oscar ResNet convolutional network, which is an encoder, which includes 3 by 3 convolution layers. And then there are 4 mask pools inside. So then why did it become 14 by 14? Because we have 4 mask pools in the middle of this. Each mask pool puts the picture down to half. Then after the 4 times equal, the 224 by 224 picture is reduced to 14 by 14. Then its output layer, it has a total of 14 by 14 points, which is as a spiral attention of the optional center of the location. And then the next one is a recurrent network, which is used LSTM, which can be based on the vector of 2, 5, 6 features of each location. Then, when you decide to translate a sentence, what should you focus on? According to the content of the image that you can concerned about, you can output the sentence by sentence describe of the image. Then the author used RNN to make 2 kinds of the attention model. We look at the figure 2, the toe rule, the deterministic statistic of the soft attention model. We see several charts. It's arranged chronologically. We look at the bottom, it has its text. This chart is corresponds to text. Call it this a bird fly over a body of water. So the white color in the figure is the area that the AI focuses on when she sees the text. For example, we see this. When we see this bird, we see the AI. He did this stare at the bird. You see the white and the slab is shining on that bird. Then when the AI says this water, we look at this machine. It really does not focus on the bird, but it looks at the background behind the bird. But your ear are black background. Indeed, this is very brave. It detected that it's a tunnel in the background. That the bottom row is the hard attention of this model. It gives out the different word corresponding to the different location of this picture. It's first by the LSTM, which tells you about such a distribution of this multiple location attention. Can describe exactly where and how it distributes. Then you select one of the 14 by 14 locations in the distribution system, and you jump out one location from 196, one as the center of your attention. Then each small figure we see it is like a small ball of gases. Then there are the center of his attention at the different times. Because it the center as a sample out. So say you, for example, you show him the machine the same picture again. He may sample a different position next time. So that is why the soft attention is about the code deterministic statistics. So what? It output one each time. It is overall one of the expectation. So it's defined unlike the follow. Also have the 3 head. It does not use the 3 head. And the row above the soft intention. It is a piecewise expectation. Its weight and sum together. For example, first small picture. He said this a woman here to throw a fly saucer. And you see the AI sees the flying saucer. The AI really focuses on the flying saucer. For example, he said that the giraffe was standing on the wood. And when she said the wood, you can see that his attention was on the location of the wood, behind the giraffe. Well, further down the feature is this LSTM model, which is a long and short-term memory model. We will talk about the architecture later, and then go down to this figure, which is an example of machine recognized of the error. This machine says it is hard. This picture is a woman holding a clock. In fact, he mistook the round logo on the t-shirt for a clock. Well, in real life, in fact, we also some sloppy people, this kind of people, he also make a similar mistake. So machine make similar mistake as people do. The following we will talk about the specific to talk about the most critical content, such a very advanced things, and how to make out. First of all, let's explain the parameters of the whole model. The big key equal to 10,000. The finish of the machine. Here we'll see 10,000 words, and the big C was the variable. What does the contemporary C stand for? Just the big C. Next motion to translate this sentence. How long is how many words? For example, when the big C equal to A, then the machine it will use its word to summarize the picture. Then it will not say words. A bird on the lake, because there are actually 4 singles. Only it take 8 singles. Then the Y is translated to the taxi. We look at this first company. The top of company on Y equal to 140. So it is the total of the whole is on order. This is a certain order for the front of to back. In total, each vector represents a word. It's on order, but each word is y1. It is a vector. It's a total of 10,000 dimensions of a vector. Each digital represents the probability that the corresponding text will appear. For example, if this time it corresponds to the word air, it has a highest probability. For example, in the middle of the example, the 3,000th position will represent the bird. Then the motion it will be the first word. It will say it is a bird because the probability of the largest one. It will output your air out. The band L is equal to this. It uses 14 times 14 equal 196 on its side. The actual it is the center of the attention. It has its 196 position. It is a square of the grid point arrow. And then we look at the second little formula in the middle of this, a equal what? The A vector, the second point, AL vector, so a set. Then this band L, we will see is equal to 196. This attention of the location. 196 location. Then each position of the attention, it can correspond of a small figure too. Then the small figure you go through this, it will extract a 512 dimension feature. It is expressed in the AI vector. The AI is called feature vector. Each position have a 512-dimensional vector. To characterize its correspondence to this small feature of this image. For example, this A vector, it represents what the attention of the upper left corner. Then it corresponds to the ResNet of the convolution network. It gives you an output of the image feature. It uses the 512-dimensional vector to express this. For example, maybe here represent a bucket of water. Then this for this L is equal to 196 position. Each position it has such a 512-dimensional image feature of the vector. So the total is 14 by 14, and the comma 512, this kind of vector is by this whole network output. You do not need this special training. You will use the training out. This on the line you can directly use. But you can also use other networks such as GoogleNet. This you can also inception that set of things. You can also use to do this image of encoder. Then this GT time is the moment t. We see that each moment it produces a word, and in the t, this moment is GT. It is this all the attention according to the different this kind of weighting. It synthesizes a vector of the image feature, which is the GT vector. Then the vector is used to produce what word should see in the TZ moment. Of course, it also depends on have been before. Then the information mainly express the vector such as a hiding state, such as HT vector and cell state. The vector of CT vector, the big one matrix is called embedding matrix. Let's introduce next part.
The model we use inverse resonance in CNN and LSTM in RNN. Let's first briefly understand what those are. What is a convolutional neural network? Convolutional neural is an artificial neural network structure which is widely used in language recognition and image processing by using convolutional neural networks. The most commonly used aspect of convolutional neural network is computer image recognition. However, because of its contention evaluation, it has also been applied in video analysis, natural language processing, short discoveries, and so on. Its goal allows computers to understand code, which is also applied to this technology. Let's take how about convolution networks work in detail. Give an example of recognizing picture. We know that a neural network is composed of series of neural networks, and there are many neurons in each neural layer. Those neurons are the key to the neural network's recognition and of things. Every neural network has its input and output wells. When the input well is a picture, what is actually input into the neural network is not those colorful patterns, but a pair of numbers. When the neural network needs to process so much input information, time that is the time where the convolution neural network can give full play to her advantage. Then chose the model convolutional neural networks. Let's first prevent the word convolution neural network from convolution and neural networks. Convolution, that is to say the neural network no longer processes the input information of each pixel, but process each small pixel error on the picture. This approach strengthens the consistency of image information, allowing the neural network to see a group instead of a point. This approach also deepens the neural networks understanding of pictures, especially the convolutional neural networks, has a batch filter that conventionally store on the picture to collect information in the picture. The information collected each time is only a small pixel error collected, and then the collected information is stored out. And the information is stored out at this time. Some edits per presentation, for example, the neural networks at this time can see some edit picture information, then use the stand state to scan the edit information generated by small similar batch filter, organize the networks, and use this edit information to summarize higher level information structures. For example, the simulated information can draw eyes and nose, and after another filter, the face information is also obtained from these eyes. The information as of all is stimulus. For example, we put this information into several layers of organized filter connected in network for classification, so that we can get the result of which category into picture can be classified into. We intersect a short section from Google's introduction to convolutional neural networks picture, and how the picture is convoluted. Below the picture of cats, the picture has three parameters of length, width, and height, and the picture has a height. The height here refers to the information used by the color generated by the computer. If it is black and white picture, the unit of height is only 1. If it is a color phone, there may be information of 3 colors, red, gray, and blue. At this time, the height is 3. Let's take color photo as an example. The filter is something that is constantly moving in the image, and it is constantly collecting small pixels in the picture to output the well after collecting all the picture. We can understand this as a picture with higher height and smaller width. This picture connects some edge information, then perform multiple convolution and in the same step, compose the length and width of the picture again and increase the height again so as to have a deeper understanding of the input picture. By abandoning the higher compressed information into a neural classification neural network, we can classify such image. The study find that with each convolution, the neural network may individually lose some information. At the times, polling can solve such problem well. In other words, we do not compress the length and width during convolution and try to retell as so much information as possible. The work of compensation is left to the mechanization, such as adding what can be ever input with the entities. With those tech, we can build a convolution neural network of our own. One of the more popular constructions is this, from the bottle to top. The first is the input image. After the convolutional layer, the convolutional information is processed by mechanization pooling. The method of mass pooling is used here. And then after the same processing, the information obtained from the second processing is passed to the two fully connected neural network connector. This is also general two-layer neural networks. Finally, a classifier is connected to classification prediction. I only give a brief introduction to image processing of convolutional neural networks. And we use the Resonance 101 model in CNN in this project, and we use connection called short-term connection, adding the residual to first train right and to get the fs equal s and gs. Resonance is built from residual block. Equal is to say that I add an addition and there is the shortcut to go there. In his own resonance, using that he is very similar to VGG. That is, it has two resonance balls. The first type is resonance ball whose height and y are higher, and that is to say the so-called. It is in the first convolutional level and the appetite is equal to 2, and then the higher and wides are higher for you. Then generally speaking, you will also double the number of channels for you. So you one by one collection will do this and increase the numbers of channels for your input. The whole thing is called resonance ball. Then you repeat things several times, and then how many resonance ball and number of your output channel are needed. You can get different resonance architectures. It is this architecture, you can see it is very similar to VGG or Google Net had 5 states. Basically, one 7x7 convolution adding a batch normalization, adding to a 3x3 pooling, and then add different resonance board. And finally, there is the global average pooling. This is the architecture of resonance. The following is the structure of resonance 101. And sequence states such as a test bit is often used in machine learning. One-to-one model, one for input connections, one for output following connection neural networks and convolutional neural networks, all built to one-to-one model, but the human brain don't has to use the one-to-one model to process time series data. And humans do not directly input the whole paragraph of text into the brain. When you read, you will read a paragraph of text from left to right and generally accurates the information of the text in your brain when writing. And after writing a paragraph, your mind will accurate the general idea of the entire paragraph. One-to-one model requires that one input corresponds to one output. For example, input a picture and output the probability value of each paragraph. One-to-one model is very suitable for image program, but not very suitable for text problem. For text problems, the length for input and output is not fixed, and a sentence can be long and short. So the length of input is not fixed, and the length of input is not fixed. For example, if you translate an English sentence in Chinese, there are 10 words in English, and there may be 10 words, 8 words, or even an idiom with 4 words. When translated into Chinese, the number of Chinese chapters output is not fixed. Since the input and output lengths are not fixed, the one-to-one model is not suitable. A better model for time series data is the many-to-one or many-to-many model. RNNs are just that. Neural the model input or output need to be fixed in length. RNN is very suitable for text to speed time series states. This is very similar to human reading habits. Every time a person reads a word, information is gradually accurate in the brain. RNN looks the word at the time and use the three vector H to add to accurate the reading information. We use wording pending to connect into an input word into a word vector S. Every time a word vector is input in RNN, and then RNN will update the stage. H accurates new inputs into a string H. H0 contains the information of the first word, and the H1 contains the first two words, the information of cat, and so on. The string HR contains the first three words, then information of the cat states, and the last state HT contain the information of entire sentences. HT can be required as from the sentences or the cat. The feature vector add a stat by set on the mat. When updating the state H, you need to use the parameter measure A. Notice the entire RNN has only one parameter A. No matter how long the chain is, there is only one parameter A. A is randomly in internet and then use the training data to learn. First, tell about simple cycle neural networks. Let's take a close look at how simple RNN combines the input word vector S into the string H. The period state is defined as HT minus 1, and the newly input word vector is designated as HT. Concatenates those two vectors to get a higher vector. This measure A is the model parameter of the RNN. This contains the product of measure A and this vector. The product of the measure and vector is a vector. Then apply this aggregation function to each image of the vector. This aggregation function is a hybrid template function. The input is any real words. The output is between the 1 to and the output of the aggregation function is used as the new state vector HT. The structural diagram of the neural networks can be understood as follows. The new state HT is a function of the period state HT minus 1 and the new input HT. The model parameter of the neural network is the new state of the metric A. HT is depend on the vector HT minus the vector HT and the metric A. LSTM is also a kind of RNN. The principle is similar to simple RNN. When the new input S is read, a new H will be output. The result of LSTM is much more complicated than that of simple RNN. Simple RNN has only one parameter matrix, while LSTM has four parameter matrices. This is comparison between of the two.
Our task is mainly divided into four parts: data acquisition, pre-process, model, and training. First, look at the data acquisition. The data acquired by the model includes two parts. The first part is the image data set, and the second part is the caption. First of all, look at the pictures. We only selected 5,000 pictures in the Coco dataset at the text. Then there is the caption, which is used to describe the content of each picture. Each picture in the image dataset corresponds to a line in the JSON file of caption. Next is to pre-process the text. Firstly, we need to create a dictionary which contains two types. Numbers corresponds to the words, and the words corresponds to the numbers. Next, we need to add words to it. If there are no such words in the dictionary, then return the unknown. Finally, output the vocabulary length. Secondly, we need to build a simple vocabulary wrapper. This is to create a counter and its default value is 0. Here to get the caption sentence of each row from the data COCO set. And here is to change the lowercase letters at the same time. The sentence tokenizer words for each captions is like this. Then assign the integer index to words in the vocabulary at the same time. Count the frequency of each word and filter out words less than the frequency. Finally, we create a vocabulary wrapper and add some special tokens. Append the start and end to each caption if there are no such word in the vocabulary. Output unknown. And the vocabulary finally contains two types. The word corresponding to the number and the number corresponding to the word. Next, we count the total vocabulary size and encapsulate the objects into files. Here is the caption path and the vocabulary path and the threshold. That means the minimum word count threshold. Here is the JSON file and here is the vocabulary file. Secondly, we need to pre-process the image. We first resize an image to the given size and resize the images in image dictionary and save into the output dictionary. Here we check whether there is output dictionary. If not exist, then create a dictionary. Here returns the list of file names in the specified folder and open the file according to the name. Here to open the picture and resize. The image is saved to the splicing path and its format is the same as the orange picture. Here we build paths for input and output dataset. In the main function, we need to define the image dictionary and output dictionary. Here is the pictures before resize. And this is the pictures after resize. The pictures pixel after processing is 256 times 256. Thirdly, let's look at the model. Given an image, in order to generate a descriptive sentence for it, our model must meet several requirements. The first one is that our model should be able to extract high-level concepts of images, such as the scene, the background, the color, or positions of objects in that image. The second one is that the generated caption must describe the image and be grammatically correct. Therefore, we logically divide the image captioning task into two modules: an image-based model and a language-based model. For an image-based model, it need to extract features and subtle differences from images. For the language-based model, it had to translate the features and objects given by the first model into the natural statements. For image-based model, we usually rely on the convolutional neural network. For the language-based model, we rely on the recurrent neural network. The following picture summarizes the methods mentioned above. This picture describes that a neural network consisting of a Bayesian convolutional neural network followed by a language generating recurrent neural network. It generates complete sentences in natural language from an input image. Tuning a good convolutional neural network from scratch is challenging and time-consuming, so we will use existing pre-trained convolutional neural network model. In this example, a pre-trained ResNet 152 is used as an encoder, and the decoder is a long-short-term memory network, as shown in the right hand. Let's look at the encoder. We first load the pre-trained ResNet 101 and replace the top fully connected layer. We here to delete the last fully connected layer and define a class where the model is saved. The input dimension of linear propagation is the input dimension of the fully connected layer of ResNet, and the output is the embed size. Here is two standardized batch. Next, we will conduct the forward propagation. The input is batch size, channel image size. We have to convert to the features. And here is to input the output of linear network into batch. And the batch size and picture size is generally 14. For the decoder recurrent neural network, we set the hyperparameters and build the layers. Here and in the forward propagation, the input features are the output of the encode. The captions are an array of captions with a length ranging from large to small, and the length is the corresponding captions. Also, the list of corresponding lengths is also a range from large to small. Next is to decode the image feature vectors and generate the captions. The embedding shape is 128. 23, 256. And then this according to the dimension 1. Here is the features shape and the embedding shape. Here the sequence so that the captions are the same length and the embeddings are the matrix of pad. The length is the length of actual useful value. In general, we first call the ResNet 101 model from touch to change the last layer of the model into a linear layer and conduct the batch normalization. Then output the features of the picture from the picture through the forward propagation. In the decoder part, while the embedding processing is carried out, the visual features obtained from the encoder are spliced with the lexical features, packaged with the lens, and then put into the long short. Per memory model to output the words. The code the first part here training. We first create a model dictionary and conduct the image pre-processing normalization for the pre-training ResNet. Here is to cascade multiple pictures to operate random crop. Next is to load the vocabulary wrapper we conducted before. And here is to build a data loader, which contains the images, the targets, and the length. Next is to build the models, which contains the encoder and the decoder, as mentioned before. We use loss and optimizer to evaluate the model. It can be said that is a loss function. Here is to standardize the list of decoders, linear list of encoders, and the encoders. To train the models, we need to set the structure length, the time step, and set a mini batch dataset. The padded sequence is a parameter of the function. The length sort from largest to the smallest. The captions sort by the length and the batch first. If set to choose the first dimension of cap is batch size. Here is to extract the image feature, and the shape is 128, 256. Here is to print the log information and output the information of each step. After training the model, we need to save the model checkpoints. In the main function, we need to define the model path. This is the path for saving trained models, and the vocabulary path. This is the path for the vocabulary wrapper, and set the crop size. This is size for randomly cropping images, and the image dictionary. This is the images that we have resized. This is a dictionary for resized images. And the caption path. This is the path for train annotation JSON file. We set the log step as 10. This is the step size for printing the log information. And we set the save step as 6,000. This is the step size for saving training models. And this is some model parameters. It is the dimension of word embedding vectors. The hiding size is 520. This is the dimension of long short-term memory hidden states. And the number of layers is 1. This is here we choose to train a total of 20 rounds here, and save every 3,000 steps. The batch size is related to the GPU. The left hand is the train model we have saved.
As a result, we have used model an end-to-end neural network system that can automatically build an image and generate a reasonable description in plain English. The model is based on a convolution neural network that echoes an image into a complex representation following by the recognized neural networks that generates the corresponding sentences. The model is trained to maximize the likelihood of the sentences given the image. We use 5,000 pictures in the common objects in context datasets as the training sets for training. In the model, we use Resonance 101 as an image actor. By first pre-training it for an image classification test and using the last hidden label as an input to the CNN decoder that generates sentences. After generates the model, we applied the corgi picture required done from the official website of VGG. Finally, we realize show attention and tell. As we know, NRN models investigatively combine CNN and RNN to slow the task of looking at picture and speaking. The model we use now is very similar to the NRN model, which is comprised of CNN and RNN. There are three main differences. The first is the CNN part of convolutional neural networks, in which Resonance is used for this model, while SNS is used for NRN. And the second part of the RNN, the model used LSTM instead of the normal RNN. For the three feature input, NRN will input the feature in each round, while the model will input the feature only once at the beginning. The reason LSTM is used here and there many different difficult tests in natural language processing can be reduced to a sequence-to-sequence framework. A machine translation test, for example, is obviously to convert one language into another, essentially to convert from one sequence of indefinite length to another. And present, the most efficient way to input sequence to sequence is LSTM, a kind of RNN with gates which can encode the source language into fixed-length vector with right semantic, and then generates the target language as the hidden state of the decode network. The image generator method is being speed by sequence-to-sequence developments in machine translation. Why not replace the source language signal with image signal so that the text of machine translation can be transferred into neural language that is image neutral language equation. In the project, loss and precision were collected as the evolution index of the model. Perplexity is a common indicator of language model, and the probability of the sentence occurring is equal to the product of the probability of each word in the sentence. Often twice equals, the loss will drop to about 1.7 and the propensity will to 2. According to the Wheel of Evolution Index, the effort of model generation is not bad. The following is a demonstration of the training process and generation effort. In fact, part of test equation generated for this project is not accurate possibility because the training dataset is not large enough. There are also many paths to input and study. Since time is limited, we will try to use a larger dataset in our spare time and replace the CNN part of the first convolution neural networks with impulses and so on, and try to compare the BLEU score of different models.